Hey everybody, in this DL we're going to actually see some equipotential lines in practice. Now usually you'd be doing this experiment yourself and we'd spend a lot of time taking our data, but unfortunately we can't do that. So instead I'm going to show you the basics of how the experiment works and how we might collect the data, and then I'm going to do the rest of the experiment off camera because it's probably not very interesting to just watch me work. Once that's done, I'm going to show you the results, and it'll be up to you to interpret them. This plastic pan is filled with a thin layer of water. If we attach these metal rings to a source of voltage, current will pass through the water from one electrode to the other. Because current is passing through the water, we'll actually be able to measure the voltage at a particular point in the water. We're going to use this to trace out equipotential lines. Remember, equipotential lines are just locations where the voltage is the same. Once I've done that, I will provide to you what the equipotential lines look like, and it'll be up to you to figure out what the electric field lines look like. If we connect the ground of the voltmeter like this, we can use a second probe to actually measure the voltage at various places. All right, let's plug in our source of voltage and see what it looks like. Let's start with the two simplest cases. If we place this probe on this electrode, we should just read the voltage that is being output by the voltage generator. And if we place it over here, we should just get 0. And we see that that's the case. But what happens if we place this probe somewhere in between the two electrodes? Well, if we place it here, I read about 1.5 volts. This makes sense. Over here, we had 3.4 volts, and over here, we had 0 volts. So we should expect that in the middle, we should get a voltage reading somewhere between those two numbers. The closer we get to the positive electrode, the higher the voltage gets. And the closer we get to the negative electrode, the lower it gets, until, as we've seen, it actually reaches 0 at the electrode itself. But if we want to find equipotential lines, we need to move to the left and right. Let's start here. Here we have a voltage of 1.24 volts. Let's see if we can find another location that has approximately that same voltage. Here's another spot that's about the same. Let's continue out this way. Here's another spot here. If we do this process a bunch of times, we can find equipotential lines in the water. But instead of actually doing all of that for all the different scenarios, I'm going to do the experiment off camera and then draw what the equipotential lines look like. But this is not a very interesting activity to make a video out of. So instead of making you watch me do this for the next 10 minutes, I'm going to do this experiment off camera and then draw what the equipotential lines look like. You're going to use that data to calculate what the electric field looks like between these two electrodes, and for the other setups described in your DL manual. All right, here's what the equipotential lines look like for the first case. This is actually all the information that you need in order to draw electric field lines. We've already discussed what the relationship is between electric field lines and equipotential lines. And if you use that relationship, you should be able to get a pretty good diagram of what the electric field looks like for this case. Remember that electric field lines always point from higher voltage to lower voltage. So to help you out, I've included the approximate voltages for each of these lines here. Here's the second case. This case is interesting because it's effectively a parallel plate capacitor. We have one plate over here that's positively charged, and one plate over here that's negatively charged. As before, all you need to know in order to draw the electric field lines is what the equipotential lines look like, and so I've included them in this diagram. Our last example is called a Faraday cage, named after the great 19th century physicist Michael Faraday. In some ways, it's much like the last example we did. There are two parallel plates that are connected to the voltage generator. But we made a slight modification. We added this round piece here. This round piece is not connected to the voltage generator in any way, but it does affect the electric fields. Why? The reason is that this round piece is a conductor. The charges inside of it are allowed to move around freely and will do so when they are exposed to an electric field. By placing this conductor in between these two plates, we're ensuring that will happen. The charges in the conductor are being exposed to an electric field and are moving around accordingly. But by moving around, they are themselves affecting the electric field. Close to these plates, we see that the equipotential lines look more or less like they would if this was not here. But closer to this round piece, we see that the equipotential lines curve around it in interesting ways. As before, you're able to use the shape of the equipotential lines to determine the shape of the electric field lines in this setup.